In lesson 2a, we found a Taylor series for sine x centered at x equals 0, which is called a Maclaurin series. The graph that you see is sine x, the black curve, along with the first 9 partial sums of that series. The first partial sum is a polynomial with order 1, or a line. You would expect the second partial sum to be a quadratic, yes, but remember sine x is odd, so there is no even polynomial. Instead, what we get is the second order polynomial is actually a third degree polynomial. Oh, a little confusing. But that's not the main point of this visual. The main point of this visual is to see the beauty of the geometry of what we're doing connected to the calculus of what we're doing and the algebra that connects the two together, which is on our paper. These polynomials were constructed to mimic the behavior of sine x near 0. How are they doing? They're doing quite well. And remember, the only information that we used to construct these, to construct the coefficients of the polynomials, was information about the sine function and its derivatives. So its first derivative, its second derivative, third derivative, all the way up, and those values at x equals 0. And not only are these curves doing a good job at approximating sine near 0, they're also doing a great job of approximating sine, well, until they kind of fail. Check out this blue curve over here. Oh my goodness, that teal curve. It basically goes all the way up to pi and then diverges away from it. Then the next blue curve, which is, the 9th order polynomial, that does a pretty good job. That's past 2 pi and then diverges off. We basically constructed an entire function by knowing its behavior at a single point. Let me say that again. We've constructed sine using polynomials just knowing its value at a specific point. But the main thing I want you to see is the convergence that happens. This doesn't happen for all Taylor series. Remember, specifically, there were a few in the first topic that we studied that only converged between -1 and 1. But notice that these polynomials are converging. The interval of convergence of the series for sine x is infinite. It just is a matter of how many of those partial sums we want to use. So again, it doesn't matter, like in this window, -1 to 1, of course it works here. Now, in the other functions, it didn't matter, those first two that we studied, it didn't matter how many partial sums we did, it would only converge for that certain window. So we'll come back to this a little bit later to understand what's happening and how we prove that. But for now, let's just take a look at the definition of a Taylor series generated by f at x equals a. And this is going to look just like the Maclaurin series that we studied, except we're plugging in an a value, and we have a polynomial that has a in it as well. And we'll write out all the terms, not all the terms, but a few terms, and then write the nth term so you could see the pattern. And I'm writing this kind of like you would write in your booklet as well. So basically we have an infinite number of terms because it's an infinite series. And I'll write it just like we did before for Maclaurin, with a k in the last Riemann sum. So that information that you see in purple is the series. Now let's talk about the Taylor polynomial. The Taylor polynomial of order n at x equals a is p sub n of x. And that's a finite series. And it's not a finite series just because writing a series and a polynomial, one is finite, one's infinite. It's an infinite series because we're saying like that if we want to write a function as a polynomial, we might need an infinite number of terms. So that's what's in purple. But then if we say, okay, I think we're good with doing like the 9th order polynomial, going back to this visual for sine, like, I think I'm pretty good. I'm pretty good with the fact that I'm going to use a ninth order polynomial to approximate sine. I'm going to use it in some sort of program that I need sine for, but sine is an expensive function, meaning that when it's used in computers or programming, that there's too much calculation going on. That process uses up too many resources, like processor speed. So we're going to instead create a finite polynomial that approximates it well enough. Like, I think we're good. I think we're good with going up to the ninth order polynomial. Then that means we're going to start at k equals 0 and go up to n, and we're going to have 10 terms. The 0th order polynomial, which is just a constant, a number, and the nth order term, which is x to the n, or in sine and cosine, it would depend on those values. Meaning sine only has the odd ones, cosine has the even ones. All right, let's take a look at two examples here. The first one, well, they're both actually fairly clean. And this first one is finding the Taylor series for e to the x at x equals 1. So right away we know that this is a Taylor series because it's not centered at x equals 0. I can easily just use this definition, but I want to show you how we would do this the same way that we have been, by writing out the first derivatives, the first few. And that looks like this, nothing different than the Maclaurin series. We're writing e to the x and plugging in 1. So that's e to the 1, which is just e. And then we'll take the derivative, which is e to the x, the only one that's like that, and plug in 1, which again is e. And then we see that this pattern goes on forever, that it doesn't matter. And we would expect that e to the x would have a pretty clean series, like one that makes a lot of sense, not much writing. And this goes on and on. In this case, however many terms we want to write is basically how specific, how approximate we want our series or our polynomial to be for this function. But obviously, if we write an infinite series, we'll get that exact function. All right, now in your booklet, we have like the space below here. So we'll just write that e to the x is equal to e plus the coefficient of e over 1 factorial, which I don't have to write, but I just show you because of the pattern. And then the third term, but the second order, is e over 2 factorial times x minus 1 to the 2. And remember, this is centered at x equals 1, so we have a transformation, a shift to the right of 1, which means we're writing in the x minus 1 format. And then we have our next term, which is e over 3 factorial, x minus 1 cubed. And that goes on forever. Now I want to take the moment to actually point out that most of our previous examples showed us, hey, find the Taylor series or find the fourth order polynomial for this function. But in this case, to write a fourth order or fifth order really is the same as finding just the general power series anyways. So we might as well write the infinite series for e. And that's because all of the coefficients are the same right here. So that's the main thing right there. All right, now we're just thinking about a way to write this as a general term, and we're writing a Riemann sum up to infinity, and we're starting at k equals 0. The reason why we're starting at 0 is because this is the 0th order, this first one right here. We could easily write it starting at k equals 1 if we wanted to. It doesn't make much sense to. And then I'm noticing that basically every power matches the factorial. That means if I use k for the factorial, I'm going to use k for the power. And that's it. E is the coefficient of every single term. K factorial is the factorial that shows up in each one. X minus 1 stays as it is because we're centered at x equals 1. If it was 5, it'd be x minus 5. And k is the power because it matches that. I'll just tell you at this point that the interval of convergence for the infinite series for e to the x is everything. And that's because it doesn't matter, just like this sine x function that we're using here, it doesn't matter the x values that we're plugging in, even though you're probably not completely sure of like, what do I mean by plugging in x values. I'm telling you that the infinite series doesn't depend on the x value that you plug in. It depends on the function that you're working with. and how many partial sums you want to go up to. So if you have an infinite number of partial sums, an infinite series for e to the x, then it's going to approximate e to the x perfectly. Same applies to sine and cosine. But again, we'll learn more of that later. And then the final example is basically approximating a polynomial with a polynomial. So it's kind of a silly thing, but we'll set it up the same way. So we got the first plugging in 1, and oh, by the way, this is at x equals 1. Okay, at x equals 1. So that's our center of approximation, and that means it's a Taylor series. So plugging in plugging 1 in for f gives us 4. You could try that out if you want to. And then taking the derivative, we have 3x squared plus 6x minus 1 at x equals 1. And we plug in that, we get 3 plus 6 minus 1, which is 8. That's the second coefficient. And f double prime is 6x plus 6. Plugging in 1 gives us 12. The third derivative is 6, and if we plug in 1, well, we can't. So the coefficient is 6. Now, we'll basically do what we did before, which is writing the third order polynomial. And one of the major mistakes that students can make in this step is to forget the factorial. So what we have is 4 plus 8 times x minus 1 over 1 factorial. And then we have 12 over 2 factorial times x minus 1 squared. And you could probably fit it, but I can't right here. We have our final term is 6 over 3 factorial times x minus 1 cubed. So that officially is our third order polynomial. We could do a little better than that, I think. We could simplify this. Definitely don't expand out x minus 1 or like the squared or cubed piece, but we could simplify those few terms there left over. And what we're doing here is we're writing a polynomial that estimates a polynomial, so it doesn't really make much sense, but I'll write it in order of decreasing degree, and we have this function. So oddly, it kind of creates a weird way that we could actually factor. We could write it in a different way, but this is our final answer, simplified. And the question I might ask, like, okay, well, what x values does this polynomial converge to the original polynomial? Well, if it doesn't converge for all x values, then we've definitely done something wrong, because to rewrite a polynomial in a different way is to write the same polynomial just factored or with different expressions or something, different terms in there that eventually add up to the same as the original. I'm kind of talking in circles because this question is kind of like a circular question. Nonetheless, that's all I have for you there. One good thing that you could do right now is to find the Taylor series for cosine x, and there's an exploration for that, or you could do it, kind of create your own. All right, thanks so much for watching.